Welcome to the deep dive. Imagine for a moment a huge skyscraper. It's totally solid, right? Invincible. Now, picture just one tiny flaw, like a hairline crack in a brick way down on the foundation. You wouldn't even see it, probably wouldn't think anything of it. But what if that tiny crack starts to spread, slowly, silently, undermining the whole thing, until, bam, the whole system, maybe a critical digital system we all rely on, just collapses. Sounds dramatic, I know, but honestly, this kind of thing happens. These hidden flaws, these vulnerabilities, they're lurking under the surface of the software we use every single day. More common than you might think. So today, we're embarking on a deep dive. We're going into that surprising and, frankly, critically important world of software vulnerabilities. Our mission, it's really to give you a shortcut, a way to get properly informed about what's actually going wrong behind the scenes with technology, why these glitches and flaws matter so much to all of us, and, crucially, how the experts find them, fix them, and try to prevent them in the first place. We're going to unpack some pretty recent big incidents. We'll explore the tech stuff underneath, but don't worry, we'll use clear examples, and we'll connect it all back to the bigger picture of cybersecurity strategy, which, let's face it, is essential today. Get ready, because I think you'll gain some insights that might really change how you look at the digital world around you. But just before we dive headfirst into all that, a quick word about our sponsor.
This deep dive is brought to you by Stonefly. They're a leader in enterprise storage, backup, and disaster recovery, AI storage, and cloud solutions. So if you're looking for secure storage, especially ransomware-proof storage, Stonefly sells air-gapped and immutable options. Really top-notch stuff for protection. You can contact sales at stonefly.com to schedule a demo. Biff checking out. All right, let's get into it. We're starting with a particularly, sneaky kind of flaw, but one that can cause massive disruption. It's called an out-of-bounds read, or for the technically minded, it's CVE-2025. So what is it? At its core, it's basically a programming mistake. The program tries to read some data from memory,
but it reads past the designated spot. It goes beyond the allocated buffer, the little box it was given.
Right. It reaches outside its assigned space.
Exactly. It's like it's supposed to read, say, 10 items from a list, but it accidentally tries to read item number 11.
And who knows what's sitting there in memory at position 11?
Precisely.
Yeah.
Could be garbage, could be part of another program's data, could be anything. It's reading unintended stuff.
Yeah, and we can make that less abstract. Think about your games console loading a saved game.
Okay.
The console expects that file to be, let's say, exactly 10 megabytes. Nice and neat. But if there's a flaw maybe in how it calculates the file size, it might try to read 10.1 megabytes.
Just a tiny bit extra.
Just a bit. But that extra bit it pulls in, it's not part of your game save. It might be corrupted data or maybe even, leftover bits from the operating system. And what happens? Your game goes haywire, textures look weird, characters walk through walls.
Or it just crashes. Straight up blue screen of death, or whatever the console equivalent is.
Exactly, that classic frustration. That can be an out-of-bounds read in action. But here's the kicker. It's not just about games crashing. That's annoying, sure. But in the wider digital world, the consequences of an out-of-bounds read are, well, they can be incredibly serious. Way beyond a glitch. When a program reads outside its lane, like that, it might accidentally scoop up sensitive data sitting in that adjacent memory.
Like what kind of data?
Oh, anything, potentially. Encryption keys that are supposed to be secret, usernames and passwords someone just typed in, confidential system settings.
Wow.
Yeah. So data exposure is a huge risk. Then there's just the unpredictable behavior. The system might become unstable, crash, leading to denial of service. And sometimes, maybe the most critical thing is that attackers can sometimes use these flaws. They can leverage that read error to actually inject and run their own malicious code.
Taking control.
Potentially, yes. Gaining control over the system. So what seems like a small coding slip-up can become a massive security hole, a gateway for attackers.
And the scary part, or maybe the important part to grasp, is that these aren't like super rare exotic bugs found once in a blue moon. Out-of-bounds reads are actually remarkably common, especially in software that does a lot of complex memory juggling.
Right. Systems written in languages like C or C++A, where the programmer is manually managing memory allocation and pointers. Those are prime territory.
Think operating systems, web servers, databases, stuff doing heavy lifting with memory all the time.
Exactly. The more complex that memory management gets, the more chances there are for a developer to, make a mistake with a boundary check or a size calculation. It's a constant challenge.
Okay, so if these are common and can be so damaging, let's talk specifics. Real-world examples really drive the point home, don't they? There was a huge one recently that definitely caught everyone's attention in the cybersecurity world. Early August 2024, the CrowdStrike incident.
Oh yeah, that was massive.
Right. CrowdStrike's Falcon sensor. This is software designed to protect computers, endpoint security. It suddenly caused widespread outages. Machines running it just started hitting the blue screen of death. BSODs everywhere, not just a few systems. This affected tons of organizations globally. A major disruption. And the root cause. What was behind it all?
Yep, you guessed it. An out-of-bounds red vulnerability in a recent update to their sensor technology.
So the very tool meant to provide security accidentally destabilized systems because of this memory error.
Precisely. And it wasn't just a minor inconvenience. This caused significant downtime. Businesses couldn't operate. Critical functions were impacted.
And serious worries about potential data exposure too, right?
Right.
Even if it was mostly system crashes.
Absolutely. Anytime a security tool misbehaves like that, you worry about unintended consequences.
Now, CrowdStrike, to their credit, they acted fast. Patches were rolled out. They did a full analysis.
They were pretty transparent about it, which helps.
True. But the incident itself, a huge, stark reminder of just how critical these memory management vulnerabilities are, even in software from top security vendors. It shows how pervasive these fundamental issues can be.
And, you know, this isn't the first time we've seen an out-of-bounds read cause global chaos. Does the name Heartbleed ring a bell?
Oh, Heartbleed. Yeah, that was huge. A few years back now, wasn't it?
Felt like yesterday in some ways. But yeah, a few years back, Heartbleed was an out-of-bounds read vulnerability, but this time it was an OpenSSL.
An OpenSSL is,
Yeah.
well, it's everywhere, right? Underpins so much secure communication on the internet, HTTPS, VPNs.
Exactly. Foundational stuff. The way Heartbleed worked was pretty clever, actually. Attackers could send these specially crafted requests, little packets of data, to servers running vulnerable versions of OpenSSL. And these packets basically tricked the server into reading more memory than it was supposed to when responding. It read past the boundary of its buffer.
So another out-of-bounds read, just triggered differently.
Precisely. And the consequence. Absolutely devastating. Attackers could pull out chunks of the server's memory, and what was in that memory? Oh, just things like the server's private encryption keys.
The keys to the kingdom, basically.
Yeah.
Allowing them to decrypt traffic.
Exactly. Usernames, passwords, session cookies, confidential data, all potentially exposed. This led to massive data leaks, widespread system compromises. I mean, countless websites, services, devices were vulnerable. Everyone was scrambling to patch.
It really underscored how one single bug, one out-of-bounds read in a critical, widely used piece of code can have just catastrophic global consequences. A tiny flaw, monumental impact. Okay, so CrowdStrike, Heartbleed, these are massive examples. It really makes you wonder, doesn't it? If these flaws are so dangerous, why do they keep happening? You'd think with all our modern tools and knowledge, we'd have stamped these out by now. What's going wrong in the development process?
That's the million-dollar question, isn't it? And the answers are often, well, kind of mundane, but critical. It often comes down to fundamental practices. Well, one of the biggest culprits, maybe surprisingly basic, is just sloppy input validation. Meaning the program takes some input, maybe from a user, maybe from another system, maybe from a file, and it doesn't properly check it.
It doesn't check the size or the format or...
Exactly. Let's say a web form expects a username that's maximum 20 characters, but the code doesn't actually check the length. So an attacker sends a username that's 100 characters long. The program tries to stuff those 100 characters into a space only meant for 20.
And boom.
Yeah.
Either it crashes or it overwrites something important or it leads to reading stuff it shouldn't.
Precisely. That unchecked input is a classic entry point for memory corruption bugs, including out-of-bounds reads, failing to validate what comes in the door.
Makes sense. What else?
Building right on that is simply missing boundary checks.
So the validation might be okay, but the code just doesn't check if it's staying within limits when accessing data?
Yeah. Sometimes developers, maybe they're under pressure, maybe the code is just really complex, they might just forget to put in an explicit check, like an if index is less than array-size check.
They assume it'll always be okay.
They assume, or it's just an oversight. In millions of lines of code, it's easy for one crucial check to be missed. And that one missing check can be the vulnerability. It's a fundamental error, but one that happens.
And are we seeing more of these or less?
Well, there's definitely a concerning trend that suggests these types of vulnerabilities might actually be on the rise, or at least they're not going away.
Why is that?
A big factor seems to be the sheer, ever-increasing complexity of modern software.
More features, more integrations.
Exactly. Think microservices, cloud-native apps, tons of third-party libraries all stitched together. Each layer, each component adds complexity.
More places for things to go wrong with memory.
Right. The interactions become harder to reason about, the memory management gets trickier, and the potential for these subtle boundary errors just grows. The scale and speed of development today can inadvertently make these fundamental mistakes more common.
Okay, so if these vulnerabilities keep popping up due to input validation issues, mischecks, and complexity, how do we fight back? What are the proactive defenses?
There's a whole range of things, thankfully, and they really need to be applied throughout the development lifecycle. One key tool is static code analysis, SAST for short.
What does that do?
SAS tools automatically scan your source code before it's even compiled or run. They look for known patterns of bad code, potential bugs, security flaws, including patterns that often lead to out-of-bounds reads.
Like a spell checker for security bugs in the code.
It's a pretty good analogy, yeah. Finding potential issues right there in the developer's environment or in the automated build pipeline. Catching them early is way cheaper and easier than finding them later.
Makes sense. But tools aren't perfect, right? What else?
Absolutely not. That's where rigorous manual code review comes in, having another human developer look over the code.
Or a fresh pair of eyes.
Exactly. Automated tools are great, but they can miss things. Subtle logic flaws, issues that arise from how different parts of the code interact. A human reviewer, understanding the context, can often spot those.
Plus, it helps spread knowledge about secure coding within the team.
Definitely. It's a crucial quality and security gate.
Okay, so that covers the code we write. But what about all the other code we use? Libraries, frameworks?
Yes. The software supply chain. That's where software composition analysis, or SCA, tools are essential.
SCA. What's its job?
SCA tools scan your project to identify all the third-party components you're using, open source libraries, commercial packages, everything. And then they check those components against databases of known vulnerabilities.
So it tells you if you're using a library that has, say, a known out-of-bounds read flaw.
Precisely. Because even if your code is perfect, if you're pulling in a vulnerable library, your whole application could be compromised. SCA helps you track those dependencies and know when you need to update or patch them. Keeping third-party stuff up to date is non-negotiable today.
Beyond the specific tools and checks, though, it sounds like there needs to be a broader philosophy, a way of working.
Absolutely. It's about embedding security into the culture and the process.
So things like secure coding training, making sure developers actually know about memory risks.
Definitely. Teams need to be well-versed in secure coding practices, especially around memory management. It can't be an afterthought.
And lots of automated testing, I assume. Build security tests right into the development pipeline.
Yes. The earlier you catch things, the better. Automated security testing should be standard practice, running constantly as code is developed and integrated.
And just continuous learning, right?
Yeah.
The threats change, so developers need ongoing education.
Couldn't agree more. Regular training on the latest risks, vulnerabilities, and mitigation techniques is vital to keep skills sharp. And, speaking of secure coding, the choice of programming language itself makes a huge difference here.
How so?
Well, languages like C and C++ give the programmer direct control over memory. Allocate this, free that, point here, point there. That power is flexible, but it's also where many of these out-of-bounds errors happen. One wrong pointer calculation, and you're reading or writing where you shouldn't.
So they're inherently more prone to these issues.
Generally, yes. They're often called memory-unsafe languages for this reason. In contrast, languages like Java, Python, C#, Rust, they have built-in memory management, garbage collection, automatic bounds checking.
The language itself tries to prevent you from shooting yourself in the foot with memory errors.
Pretty much. It handles a lot of the dangerous stuff automatically, making them memory safe, or at least safer. They're significantly less prone to classic out-of-bounds read-write bugs in the code written in that language. But there's a really important warning here, a big caveat.
Okay.
Even if your main application is written in, say, Python, which is generally memory safe, it might use third-party libraries or extensions that are actually written in C or C++E.
So the underlying components could still be vulnerable.
Exactly. You might have a Python library that, under the hood, calls a C function to do some heavy lifting faster. If that C code has an out-of-bounds vulnerability, your Python application can still be exploited through it.
So you still need to be careful about your dependencies, even with safer languages. The whole supply chain matters.
Tremendously. You have to look at the whole stack.
And regardless of the language, it sounds like just being incredibly careful with numbers is key.
Yeah.
Like buffer sizes, lengths, offsets.
Meticulous is the word. Every calculation related to memory size or position needs to be double and triple checked. especially when dealing with data coming from outside the program untrusted input.
You mentioned sentinels earlier, like NUL characters and C strings. Why are they tricky?
Right. In C, a string is just a sequence of characters ending with a special invisible character called NUL. Many functions rely on finding that NUL to know where the string ends. If an attacker sends input that's missing the expected NUL terminator, a poorly written function might just keep reading past the end of the allocated buffer, looking for a NUL that isn't there.
Reading and reading.
Yeah.
Potentially exposing lots of memory.
Exactly. It's a classic way to trigger an out-of-bounds read. So you have to be super careful about trusting assumptions like, this string will always be NUL terminated when the data comes from an untrusted source. Validate everything. Be paranoid. So we've talked about prevention. What about actually catching these bugs if they slip through?
Yeah, detection tools. You mentioned static analysis earlier, finding bugs in the code before it runs. What else?
Well, once the software is running, dynamic analysis tools are really powerful. A great example is Address Sanitizer, or often called ASAN.
How does that work?
You compile your code with ASAN enabled. It adds extra checks around memory accesses. Then, when you run the program, if it tries to read or write outside a valid memory region, boom. ASAN detects it immediately and gives you a detailed report, often pinpointing the exact line of code causing the problem.
Like a runtime memory watchdog.
Exactly.
Yeah.
Incredibly useful during testing and even sometimes in production, carefully managed. And another really effective technique, though it sounds a bit chaotic, is fuzzing.
Fuzzing. What's that?
Fuzzing is basically throwing tons of random, unexpected, or deliberately malformed data at a program to see if you can make it crash or behave strangely.
Just bombarding it with junk?
Sort of. Intelligent junk, often.
Mhm.
Fuzzing tools generate vast amounts of varied inputs. Really long strings, weird characters, invalid file formats, anything that might stress the program's input handling logic.
Trying to hit those edge cases that normal testing might miss.
Precisely. Fuzzing is fantastic at uncovering hidden bugs, including out-of-bounds reads that only trigger under very specific, weird input conditions. It's like automatically banging on the software in millions of different ways until something breaks.
Okay, this is fascinating. Understanding the bug, how to prevent it, how to find it. But then there's the reality of managing these vulnerabilities when they're found in critical systems people rely on every day. Which brings us to some recent news from Citrix. NetScaler ADC and NetScaler Gateway. These are really common products in enterprises, right? For secure access and application delivery.
Very common, widely deployed.
And in June 2025, they disclosed a couple of pretty serious vulnerabilities, which really highlights this ongoing battle.
Yeah, and one of them, CVE-2025-5777, is directly relevant to our chat. It's rated critical, CVSS score 9.3. That's really high.
And what is it?
It's described as insufficient input validation leading to memory overread. Sound familiar?
An out-of-bounds read. Again.
Bingo. This one specifically affects systems set up as gateways, think VPNs, remote desktop proxies, or as AAA virtual servers, handling authentication, authorization, and accounting.
So, core security functions.
Absolutely. And the risk. Successful exploitation could let an attacker read sensitive stuff from the device's memory. We're talking credentials, session data, configuration details, potentially very damaging.
And there was another one too, right? Not an out-of-bounds read, but still serious.
That's right. CVE 2025-5349, high severity 2, 8.7. This one was about improper access control on the management interface. Meaning an attacker who could somehow reach certain management network interfaces could potentially bypass normal security and gain unauthorized access to control the device. Not good either.
Definitely not. So two different kinds of serious flaws hitting these critical devices.
And what makes these particularly worrying for organizations using NetScaler is that they can likely be exploited remotely, over the network.
An attacker doesn't need to be inside already.
Correct. Which puts a lot of enterprise networks at risk. Citrix released patches, of course, and listed the specific versions affected 14.1, 13.1, and others need updating. They also specifically warned about older versions like 12.1 and 13.0, which are end of life but still vulnerable. People really need to get off those unsupported versions.
So the advice is patch immediately.
Patch immediately. And they also noted a critical step after patching. You need to terminate all active user sessions, like ICA and PQIP, to make sure everyone reconnects through the newly secured code.
An important detail. And people using Citrix cloud services.
They're covered. Citrix manages the patching for those automatically. which is one advantage of cloud services sometimes.
And just quickly, they fixed a couple other things too. Privilege management flaws.
Yeah, CVE 2025-0320 and CVE 2025-4879, both high severity, related to letting attackers gain higher privileges than they should have on Windows machines running Citrix client software.
So a whole batch of serious issues. It really shows the constant pressure vendors are under and the vigilance needed by IT teams. Memory errors, access control flaws, privilege issues. It's a multi-front battle.
Okay, so vendors find flaws, they release patches.
Yeah.
Simple, right? Just install the patch.
Oh, if only it were that simple in the real world.
Exactly. Let's talk about the reality of patching. The unseen battle in IT departments. We saw this great, very relatable discussion online. I think it was on Reddit. An IT admin was venting, basically saying something like, your patch guy is a moron if patches take hours.
Yeah, you hear that frustration.
This admin was dealing with patches supposedly taking 4 hours, causing servers to go into a hung state, unresponsive, requiring multi-day staging. Just a nightmare scenario.
That's painful and probably indicative of underlying issues. And their specific dilemma was, how do you patch something critical like one of their Citrix data collectors, XDCs, without messing up user connections? They had 4 of them. The options they saw were either pulling the server out of the load balancer on the NetScaler or just disabling all the Citrix services on the server before patching. Both risky for uptime. Right, that's the classic patching tightrope walk, balancing security urgency with operational stability. And the feedback from others in that discussion was really insightful. The general consensus was, yeah, a 4-hour patch time for something routine like Citrix. Something's likely wrong with the process or the environment.
Not the patch itself, necessarily.
Probably not. Unless the systems were incredibly far behind on updates, routine monthly patching should be much faster, maybe 30 minutes to an hour per server.
So what were the suggestions for doing it better?
Well, a common strategy mentioned was the odds and evens approach. Patch half your servers, say the odd-numbered ones, one day, then the other half, the even ones, the next day, preferably during off-peak hours.
Staggering the impact. Exactly. Ensures service continuity. Also, techniques for isolating the servers gracefully. Using load balancer features to drain connections and take a server out of rotation cleanly before patching. Or for systems like Citrix Provisioning Services, PVS, simply disabling the target server in the management console before you touch it. Consistency and automation are key.
That discussion also got into infrastructure sizing. The admin had 4 of everything data collectors, PVS servers, storefront servers. Was that too much? Over-provisioned.
Ah, the eternal debate. Some might say yes, maybe you only need 2 or 3 for the load, so 4 is extra cost and management.
About the counter-argument.
Redundancy, especially if those servers are spread across different physical locations or data centers. Having N+1 or even N+2 capacity means you can lose a server or even a whole site and potentially still maintain service.
So it's not just about handling load, it's about resilience, being able to survive failures or maintenance.
Precisely. It's a strategic decision balancing cost efficiency against risk and required uptime. For critical services, resilience often wins out.
And the key to making that work, being able to patch or reboot servers without users noticing, is proper load balancing, right?
Absolutely critical. If your storefront servers and delivery controllers are properly load balanced, you should be able to take one offline for maintenance during production hours, and users shouldn't even notice. Traffic just gets redirected to the remaining healthy servers.
That capability changes patching from a major outage event into just routine maintenance.
That's the goal. Seamless operations. And automation plays a huge role here too, especially in big Citrix environments. Tools like machine creation services, MCS, were mentioned.
How does MCS help with patching?
Instead of patching hundreds of individual virtual desktops or application servers one by one, you patch a single master image, the gold image.
Patch it once in the template.
Right. Then you update the machine catalog to use the new image and schedule reboots for the virtual machines. When they restart, they boot from the clean, patched gold image.
Much more efficient and consistent.
Massively. It streamlines the whole update process for large numbers of virtual machines. Image-based management versus individual patching.
So listening to all this, the bugs, the patches, the operational hurdles, what's the takeaway for you, the listener? Understanding these deep dives, even the technical bits about out-of-bounds reads or the specifics of Citrix patching, it really equips you. It helps you make sense of the digital world, ask better questions about the services you rely on, evaluate security claims more critically, and when you see headlines about breaches or outages, you have a much richer context for understanding why it might have happened, and how complex fixing it can be. You're not just seeing the tip of the iceberg.
And it all reinforces that core idea.
Hmm.
Cybersecurity isn't a destination. You don't just achieve security and you're done. It's a continuous process. Constant vigilance, rigorous patching, yes, but also evolving practices, ongoing learning, adapting to new threats. It's about building resilience, not just strong walls, expecting things to break sometimes, and being ready to respond.
Okay, let's broaden the scope a bit now. Let's talk about another key part of the digital perimeter, VPNs, virtual private networks, and also the fundamental concepts of AAA authentication, authorization, and accounting. So VPNs. Most people have probably used one, especially with remote work being so common. They create that secure, encrypted tunnel over the internet, right?
That's the basic idea, letting remote workers connect securely back to the company network, protecting data from being snooped on while it travels across the public internet, usually requires logging in, authenticating first. But here's the crucial security point. VPNs themselves are a huge target for attackers, a prime attack vector.
Why is that? Because they're the doorway in.
Exactly. If an attacker can compromise the VPN gateway itself or steal valid user credentials for the VPN, they potentially get a direct encrypted tunnel right into the heart of the organization's network, bypassing other perimeter defenses.
So the security of the VPN endpoint and the user accounts is absolutely critical.
Paramount. It's not just about the encryption strength.
Which means if you're choosing a VPN provider, either for yourself or your company, you need to be really careful. Do your homework.
Absolutely. Due diligence is key. What's their reputation? Have you done a risk analysis? How often do they patch their systems?
Have they had recent security scares? Zero-day vulnerabilities found in their software?
All crucial questions. And be especially wary of some free VPN services. They often cut corners on security or privacy, or sometimes their business model is selling user data. You often get what you pay for, or less. And another thing about VPN providers, logging. What information do they keep about your connections?
That's a big privacy concern, right?
It is. Many providers log something, maybe your real IP address, connection times, how much data you transferred. You need to understand their logging policy, because if the VPN provider gets breached, all that logged data about you or your employees could be exposed. Even if your actual traffic was encrypted, the metadata leak can be damaging.
So it's a trade-off. Sometimes you need logs for troubleshooting or security audits, but they also create risk.
A very delicate balance.
Okay, so VPNs encrypt traffic, provide remote access. But what don't they do? What are their limitations? This is important.
Yeah, they're not a magic bullet.
Right. Like, they don't stop phishing, do they? If someone tricks a user into giving up their password.
Nope. The attacker can log into the VPN with those stolen credentials just fine. The VPN sees a valid login. Social engineering bypasses the encryption.
And they don't fix weak passwords either. If your password is 123456, the VPN doesn't help.
Doesn't help at all. Still needs strong passwords and ideally multi-factor authentication, MFA, layered on top for any VPN access.
What about malware? Does the VPN stop viruses?
Not inherently. Malicious files or data can travel through the encrypted VPN tunnel just like any other data. If you download a virus while connected to the VPN, you still get the virus.
So you still need endpoint protection, antivirus, and just generally be careful about what you click and download. VPN doesn't replace basic security hygiene.
Exactly. It's one layer, an important one for transit security, but not the whole story. So given all that, what are the best practices for using VPN securely?
Continuous monitoring seems key, keeping an eye on your VPN provider and your own VPN gateways.
Definitely. Regular risk assessments. And adopting a zero-trust mindset is crucial. Just because traffic comes over the VPN doesn't mean it should be trusted implicitly. Verify everything.
Principle of least privilege for access. Only give VPN users access to the specific resources they need.
Absolutely. Combine that with strong individual authentication and mandatory MFA. No shared accounts.
And logging. You mentioned the risks, but is some logging recommended?
Generally, yes. Logging high-level session info, who connected, when, from where, for how long, is usually necessary for auditing and incident response. Just be mindful of what you log and how you protect those logs.
Okay. And demanding strong encryption, testing for leaks.
Yes. Use strong, modern protocols. Regularly test to make sure the VPN isn't accidentally leaking your real IP address or DNS requests.
Some solutions combine firewalls and VPNs too.
Right. Firewall rules can restrict what VPN users can actually reach even after they connect, adding another layer of control beyond just the encrypted tunnel.
And there are tools that can help find vulnerable VPN setups, scanning for open ports, and specific services.
Yeah, security scanners can identify open VPN ports like IKE, open VPN ports, and even fingerprint the specific VPN software running, like Fortinet or Ivanti.
Which helps defenders find systems needing patches for known flaws, like those big FortiGate or Ivanti vulnerabilities we saw recently.
Exactly. Knowing what you have exposed on your perimeter is step one to securing it. Okay, that nicely sets up our transition to AAA, authentication, authorization, and accounting.
The 3 pillars. Sounds fundamental.
It really is. It's a core framework used everywhere in cybersecurity to control access effectively. It answers 3 basic questions. Who are you? What are you allowed to do? And what did you do?
All right, let's break them down. First, A, authentication. That's the who are you part, right? Proving your identity.
Correct. Verifying that the user or the system claiming an identity is actually who or what they claim to be. Is this really Jane Doe logging in? And authentication usually relies on one or more of 3 types of factors. Something you know, something you have, or something you are.
Okay, something you know. That's passwords, PINs, security questions.
Exactly. Knowledge-based, easiest to implement, probably most common, but also generally the least secure because knowledge can be shared, stolen, guessed.
Right, something you have.
That's possession-based. An access card, a physical key, a hardware token like a YubiKey. Maybe a one-time code generator app on your phone. You need the thing to get in.
Better than just knowing something, but the thing can be lost or stolen.
Correct. And the third factor, something you are.
Biometrics. Fingerprints, face scans, iris scans.
Yeah. Inherence-based. Using unique physical characteristics. Generally considered the most secure because they're hard to fake or steal, though not impossible, and can be expensive to implement widely. Fingerprint readers can sometimes be fooled, for example.
So no single factor is perfect, which is why we have
Multi-factor authentication, MFA, or 2FA for 2 factors.
using more than one type of factor at the same time.
Exactly. Require a password, something you know, plus a code from your phone app, something you have. An attacker needs to compromise both factors, which is much harder.
Or for really high security, maybe add a fingerprint scan too. Something
You could. Layering different types of factors provides the strongest authentication. Password plus token plus biometric is very robust, makes a breach much less likely. Okay, so once authentication has confirmed who you are, the next step is authorization, the second A.
Which answers, okay, you're Jane Doe, now what are you allowed to do here?
Precisely. Authorization determines your permissions, your access rights, based on your confirmed identity.
Like in an office building, your authenticated key card only opens certain doors. A junior person can't get into the CEO's office.
Perfect analogy. Same in the digital world. Just because you're authenticated onto the network doesn't mean you can access everything. Your user role might only grant you access to specific file shares, applications, or databases relevant to your job.
So it enforces the principle of least privilege after you're logged in.
That's exactly what it does, verifying permissions for every requested action or resource access.
All right, authentication, who you are, authorization, what you can do. What's the final A? Accounting.
Counting answers. What did you do while you were logged in?
Tracking activity, logging.
Exactly. It's about monitoring and recording actions performed by the authenticated user. Login times, logout times, resources accessed, changes made, commands run, creating an audit trail.
Linking actions back to a specific user.
Critically important. Because accounting is essential for, well, lots of things. Business reporting, capacity planning, security monitoring, compliance audits, and crucially, accountability.
Accountability.
Yeah.
Like catching someone doing something malicious.
Precisely. Let's say that disgruntled employee we mentioned earlier deletes important files. The accounting logs should show exactly which user account deleted which files and precisely when.
Invaluable information for investigation, maybe legal action, and figuring out how to prevent it happening again.
Absolutely. Even if you can't prevent the initial act, the audit trail provided by accounting is incredibly valuable for response and remediation. It provides visibility and proof.
Okay, AAA makes perfect sense as a framework. Now, how does this tie into the practical world of maintaining systems? Let's go back to NetScaler upgrades as an example. This isn't just patching, it's a bigger operation.
Right. Upgrading the entire system firmware definitely requires careful planning.
And the documentation stresses those before you begin steps, doesn't it? Read the instructions carefully.
That sounds basic, but vital.
Back up everything. Configurations, licenses, maybe even a full system snapshot.
Non-negotiable. Backups are your safety net if anything goes wrong during the upgrade.
And download the correct firmware version for your specific model and current setup.
Getting the wrong file can cause major headaches. Due diligence up front saves pain later. And then the upgrade itself. NetScaler offers different ways to do it right.
Yeah, mention the GUI, the graphical interface, point and click.
Probably easiest for many admins for occasional upgrades.
The CLI, the command line interface, good for scripting or automation.
Or for admins who just prefer the command line, faster for some tasks.
And the Nitrio API for deep automation, integrating upgrades into larger orchestration workflows.
Right, options to suit different environments and skill sets.
But the job isn't done when the progress bar hits 100%, is it? That post-upgrade verification seems absolutely critical.
Oh, absolutely. Never assume an upgrade worked perfectly without checking.
What kinds of things need checking?
Confirming virtual servers are back UP and serving traffic, making sure the health monitors for back-end services are working correctly.
If you use GSLB, global server load balancing, making sure the sites are synchronizing properly across locations.
Crucial for geographically distributed services. And verifying licenses are still valid and all your SSL certificates are present and working.
Basically, a full health check to ensure the system is stable and secure after the change. Don't skip this step.
And it's not just about major upgrades. Staying current with smaller updates and patches is an ongoing thing.
That check for update feature is there for a reason.
Right. Updates bring not just security fixes, but often performance improvements, new features, stability enhancements. Keeping reasonably up to date is just good practice for performance and reliability, as well as security. Reading the release notes helps you know what you're getting.
So bringing this all together, we've gone from the nitty-gritty of out-of-bounds reads, seen their impact in huge incidents like CrowdStrike and Heartbleed. We've looked at specific new threats like the recent Citrix flaws, dug into the real-world messiness of patching, explored VPN security, and unpacked the AAA framework. What does this journey through the depths of system vulnerabilities really mean for you listening right now? Hopefully it empowers you, gives you that sharper perspective to navigate our complex digital world, to ask better questions, evaluate security claims more critically, and understand the news with deeper context.
And it really underscores that cybersecurity isn't a one-and-done task. It's that constant process. Vigilance, patching, evolving practices, learning, adapting, building resilience, which leads to a final thought to maybe leave you with. So what does this all mean? In a world where, as we've seen, even a single misplaced character in code can bring down critical infrastructure or expose sensitive data, this deep dive into system vulnerabilities reveals something pretty profound, I think. Security isn't just about building strong walls around things. It's also about the constant vigilance, the meticulous management of every tiny detail inside those walls, and maybe most importantly, the human element, the continuous learning and adaptation. So the question for you is, how prepared is your digital world for the unexpected, and what overlooked small detail might actually be its biggest risk? Something to think about.
Definitely something to think about. We hope this deep dive has given you valuable insights into the complexities behind the scenes. And a final thank you to our sponsor. This deep dive was brought to you by Stonefly, your partner in enterprise storage, backup and disaster recovery, AI storage, and cloud solutions. For secure, ransomware-proof storage with air-gapped and immutable solutions, reach out to them. Visit sales@stonefly.com to schedule a demo and explore how Stonefly can protect your most critical data. Thanks for joining us on the deep dive.